Okay, after the graphical overview in the last video, let's dive into the nuts and bolts of how this actually works. So let's use that same example. Let's look at a function like 2 square root of x. Okay, so previously if we had wanted to find the area underneath this curve, if we'd wanted it to go from like 1 to 9, think all the way back to the Riemann sums, and we would have split this up into a bunch of rectangles. And here's a typical one of them. And the base of that rectangle would have been dx, a little change in x, and the height of that rectangle would have been f of x. 2 squared x in this case, but so when you talk about the area of one of these rectangles, it's literally height times width. There's one rectangle, and then you use the magic s, the integral function, which makes all of those rectangles infinitely skinny and infinitely many of them and adds them all up, and voila, you have the exact area under the curve. So now we're changing our geometry, but the calculus is essentially still going to be the same. So we now want to visualize taking this rectangle and the curve and spinning everything 360 degrees around the x-axis. So the whole thing spins around and gives you this sort of disc shape. I'm going to redraw that because that's a terrible drawing. So when you spin that typical rectangle around, it gives you a disc shape. It looks something like this. You can see why I use the app, because my skills of an artist are not that great. And the x-axis would still be coming through there. So really we just need to change our area of a rectangle formula into the volume of a disk formula. And so let's talk about the volume of this particular disk right here. That's a three-dimensional shape. It is volume. But like a lot of three-dimensional shapes, it's the area of the top, or the side, I guess in this case, times the depth. So the area of this part, it's a circle. So that's going to be pi r squared. And I should point out that the radius, the r of this, is just the function value. So it's pi f of x squared. And then the thickness of this disk is still dx. So the volume of one disk is pi f of x squared dx. And then again, we just use the magic s, the integral, which gives you infinitely many, infinitely skinny disks, all added up. So let's see if we can actually work that out on our particular example here. So let's get that bit out of the way, and let's do 2 squared x. So we want the volume of this shape from 1 to 9. And we want pi radius, which is, again, radius is just given by the function value here. So pi radius squared thickness of the disk. Okay, so there's our full volume formula. You've probably never been so glad we were integrating a square root function, because as we simplify this algebraically, we get 1 to 9. I'm going to pull the pi out front because that's just a constant multiple. But squaring this part gives you 4x. dx, and this is easy integration. We've got pi, and 4x integrates to 2x squared. Evaluated from 1 to 9. No problem. I'm going to switch the 2 and the pi order. So 2 pi plugging in 9 would give you 81 right there, minus 2 pi plugging in 1 would give you 1. So we get 162 pi minus 2 pi for a total volume of 160 pi. And if we had units on this, keep in mind this is volume. So this would be like cubic inches or meters or whatever we're in. Okay. So that's the basic idea. It's still just integration. It's just we've switched our basic f of x times dx, which gives you a rectangle, into pi f of x squared dx, which gives you a disk. And I'd like to point out that we kind of get two techniques for the price of one here. Let me do a little bit of erasing up here. And let's say that instead of just wanting the area under the curve rotated around, let's say we wanted to get the area between two curves. So I'm going to put another curve in here, another function. So let's say this function is just a line, just 1/2 of x. And let's say now that we're interested in spinning the area between these two around. So a typical rectangle now is going to look like that. And when you rotate that around, you're not going to get a solid disk anymore as you rotate this around. There's going to be a hole in the middle, right? So this is going to be a hole right here. So you get more of a washer. So that's why this section is called the disk washer method. It's just a washer if you're getting the area between two curves and rotating them around. So that gives you this washer, this hole in the middle. And really the beauty of this is there's not much modification that's needed here. We're really still just going to find the total volume as though there were no hole in the middle. And then we're going to subtract off the middle part. So let's say that, let's go back to our original integral here and just say the solid shape would be this pi r squared, and we just want to subtract off the middle part, which is also a pi r squared. And that integral will give us the volume of this shape with the hole in the middle. So we would do the first part right here, just like we did. We already know that part gives you 160 pi. And then we just do this part, which I'm not going to actually work out, but that's an easy integral to do as well. And when you subtract the two results, this 160 pi minus whatever you get there, that will be the volume of this shape that comes from the red line minus the yellow line rotated around 360 degrees. Okay, we'll look at a couple homework examples in the next video.